Satellite orbital motion. The motion of the Earth and other things around the Sun is referred to as orbital motion. Orbital motion happens when an object moves ahead while being dragged by gravity toward another object. Any object that orbits the Sun, Earth, or other huge body is referred to as a satellite. Natural satellites and man-made satellites are the two types of satellites. Natural satellites include the Moon, planets, and comets. Satellite motion, like that of any projectile, is governed by Kepler's laws of orbital motion. Kepler's laws of orbital motion. Kepler's laws of orbital motion are laws describing the motions of the planet's orbit in the solar system. Our greater understanding of this planetary motion could not be possible if it weren't for the work of a German mathematician named Johannes Kepler. Kepler firmly believed in the heliocentric Copernican model of the solar system, which rightly placed the Sun at its center. He also learned that the reason Mars' orbit was problematic because the Copernican system wrongly assumed the planet's orbit to be circular. He later then realized that the orbits of the planets are not circles, but rather the elongated or flattened circles known as ellipses. Which brings us to his first law, also known as the law of ellipses. The first law states that each planet that moves around the Sun is in an elliptical orbit where the Sun is located at one of the foci of the ellipse. The planet follows the ellipse in its orbit, which means that the distance between the planet and the Sun changes as the planet travels around its orbit. Moving on to Kepler's second law of orbital motion, sometimes called as law of equal areas. It describes the way an object's speed varies along its orbit. Planets do not move with constant speed along their orbits. Their speed changes so that the area of space they create with respect to time would be equal. When the planet is close to the Sun, the stronger the Sun's gravitational pull will be on it, thus making the planet move faster. On the other hand, when a planet is far from the Sun, the slower the planet moves since the Sun's gravitational pull will be weaker. The third law of Kepler's orbital motion is the law of harmonies, which implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. Therefore, the farther the planet is from the Sun, the longer the path it will take, and the longer time it has to complete its orbit, since it will travel slower because of the weaker gravitational pull of the Sun on it. For example, Mercury, the innermost planet, which is closest to the Sun, is faster to orbit than the Earth because it has shorter path and the Sun's gravitational pull on it is stronger compared to the Earth. Orbital perturbations. Orbital perturbation is a phenomenon in which the orbit and satellite or celestial body is altered by one or more external influences. Perturbations can be classified based on how they affect the Keplerian elements. Number 1. Secular variations. Secular variations is referred to as the Earth's magnetic field is slowly changing on timescales that range from years to millennia. Number 2. Short period variations and long period variations. This affects the weather and climate duration depending on time length. When satellite is near to external bodies such as Sun and Moon, it receives a stronger gravitational pull that causes the orbital inclination of the geosynchronous satellite, which changes over time. This would increase orbital inclination from 0 degrees at launch to 14.67 degrees in 2.6 years. The forces pertaining to orbit perturbations are: number 1. Gravitational force of the Sun. The Sun's gravitational attraction is the main force acting on each planet. Number 2. Solar and lunar eclipse. A satellite is said to be eclipsed when Earth or Moon prevents sunlight from reaching it. A satellite draws electrical energy for its housekeeping with the help of the solar panels. Eclipses affects the working of the satellite because it will not receive power from its solar panels due to sunlight obstruction. Number 3. Solar radiation pressure from the sun rays. Perturb the satellite orbit and the satellite experiences change in eccentricity of orbit. The eccentricity builds up for 6 months and then shrinks during the next 6 months. Number 4. Atmospheric drag. These satellites' orbits are influenced by atmospheric drag, which causes the satellite to fall into the lower atmosphere, but it is neither incinerated by air friction or falls to the planet's surface. Number 5. Aerodynamic drag. Aerodynamic force is exerted on the satellite in the opposite direction to its velocity. The aerodynamic drag is very significant at low altitude, about 200 to 400 kilometers. It is because of the very high velocity. Number 6. Asymmetric gravitational field due to the Earth's oblateness. The shape of the Earth and many other bodies is not perfectly spherical. Venus, Jupiter, and Saturn are the planets that perturb the Earth's orbit. Astronomers now utilize high-speed computers to calculate orbits in multi-body systems such as the solar system. The computers may be configured to account for significant disturbances in all of the member bodies' orbits. Orbit determination and dissemination. The satellite orbit determination method estimates discrete observations of an orbiting object's position and velocity. The measurements from the space-based GPS receiver (GPSR) on the object are included in the collection of observations. The future state of motion of an object whose orbit has been known from past measurements is estimated using satellite orbit dissemination. A set of approximate equations of motion describe the motion of the satellite. The degree of approximation is determined by how orbital data is intended to be used. Because observations are subject to systematic and random errors, orbit determination and dissemination are probabilistic processes. External forces such as terrestrial gravity, atmospheric drag, multi-body gravitation, solar radiation pressure, tides, and spacecraft thrusters all have an impact on the satellite. The accuracy and precision required from the orbit determination procedure, as well as the amount of accessible data, influence the forces used in modeling. The nonlinear dynamical equations come from the intricate modeling of these forces. The accuracy and precision of the object state that may be calculated are limited by a number of physical and computational errors. Similarly, observational data are inherently nonlinear with respect to the object's state of motion, and some influences may have been overlooked in models of state of motion observation. Comprehensive force models availability of ground-based tracking devices, high precise time and frequency standard, and high accurate station coordinates in relation to a well-defined reference frame are all required for satellite orbit determination. The orbit solution may be skewed to some extent by errors in each component. The following areas are now limiting the precision of satellite orbit determination. Modeling of non-gravitational forces, such as solar radiation pressure, Earth radiation pressure, and antenna thrust. Modeling of satellite attitude control, time variable gravity field, antenna phase center corrections, ionospheric activities, and tracking data quality associated with clock stability.